All right, let's dive right into this explainer. If you've been following the tech world lately, you have absolutely seen the wild headlines about SpaceX's StarMind project. The grand plan to put massive data centers up in orbit. But today, we are totally skipping the hype. We're going to use fundamental physics and just raw economics to figure out if this is actually the future of computing or, well, something else entirely. The whole pitch kicks off with this absolutely mind-boggling number: 1 million satellites. Back on January 30th, 2026, SpaceX filed an application with the FCC for up to 1 million of these orbital data center satellites. And the public promise? It's huge. They're basically claiming they can solve Earth's crushing AI energy crisis by capturing continuous solar power in space. No terrestrial grid, zero land constraints. I mean, it literally sounds like science fiction rapidly coming to life, right? So here's where things get really interesting. When you look at the reactions, both the credulous believers and the cynical doubters are, well, completely wrong. And to figure out why, we have to totally break down our basic intuition about space. See, the believers think space is this magical realm of endless free cooling and unlimited sunshine. And the cynics? They just think the whole thing is a massive vaporware stunt to prop up the stock price. But honestly, neither of those views actually survives contact with the physical reality or the financial filings. To get to the truth, we've got to correct our physics first. Just think about these staggering proportions of the actual machine SpaceX intends to build to pull this off, the AI-1. This thing has a massive 70-meter wingspan. That makes it wider than a Boeing 747-8 aircraft. And get this, all that size is just to keep a single rack's worth of silicon alive in orbit. Why on earth would one rack of GPUs need 600 square meters of solar panels and 110 square meters of radiators? Well, it all boils down to a massive misunderstanding about the temperature of space. Okay, first things first, we need to completely shatter the myth that space is some kind of cosmic freezer offering free cooling. It absolutely isn't. Because a vacuum removes convection, meaning there's literally no air to blow across a heat sink, and it removes conduction, so there's no fluid to dump heat into. So what does that mean? It means space acts exactly like a giant thermos. Seriously, if you wanted to design the most thermally isolating environment known to human engineering, you would build a hard vacuum. And that is exactly where these data centers are forced to operate. Right, so because of that giant thermos effect, to even survive up there, the satellite has to use something called radiative rejection. Since you can't just blow a fan over a heatsink, you have to convert your waste heat into infrared photons and literally throw them out into the void of space. This entire process is governed by the Stefan-Boltzmann law, which basically says that radiated power scales with the fourth power of temperature. What does that mean in plain English? It means the only way this machine doesn't melt into slag is by running incredibly hot, so it can literally glow its waste heat away. But here's the kicker. Despite what a ton of skeptics have been claiming online, SpaceX's thermal math actually works. A lot of published critics wrongly assumed these satellites would use single-sided radiator panels, which, would mean they'd melt. But SpaceX's design uses double-sided radiators, and they orient them edge onto the sun, so both faces are looking out at the cold, deep sky. When you actually run those numbers, getting a surface temperature of around 48 to 67 degrees Celsius is completely reachable. So the intense heat dictates the massive, sprawling shape of the machine for sure, but it doesn't ruin the plan. The thermal engineers definitely did their homework here. Okay, so the heat math works out great. But that brings us to the second pillar of their pitch, the claim that it's always sunny in space. Well, that comes with a massive catch. For a typical satellite in low Earth orbit, it spends a third to a half of every single 90-minute revolution in the dark, in the Earth's shadow. That always sunny claim, it only actually works in a very specific, super narrow orbital lane called the dawn-dusk sun-synchronous orbit, which permanently rides the day-night terminator line. And this strict physical limit means there is very, very little of this beachfront orbital property available. Independent estimates suggest you can only pack about 10 gigawatts of total compute into this golden orbit safely. 10 gigawatts. Now compare that to SpaceX's target of adding 100 gigawatts to orbit every single year by 2030. Because there simply isn't enough room in that always sunny lane, the vast majority of a 1 million satellite constellation would have to fly in normal orbits. That means they'd have to carry incredibly heavy batteries and endure brutal thermal cycling in and out of the sun. And that completely ruins the incredible efficiency that justified going to space in the first place. And wow, that brings us to the sheer weight of it all, the mass problem. If they actually want to deploy 100 gigawatts a year using the AI-1 satellite's actual payload specs, the freight requirement is a staggering 1.43 million tons annually. To put that into perspective for you, that is 414 times SpaceX's own record-breaking launch mass from 2025. Actually, scratch that. It gets crazier. It's over 60 times the weight of every single object humanity currently has in orbit combined, launched every single year. Let's just let the numbers do the talking here. To hit that 2030 goal, SpaceX would need 14,290 Starship flights a year. That implies a flawless launch every 37 minutes, around the clock, 24/7. Think about how completely fantastical that cadence is for a vehicle that, as of August 2026, has 0 orbital flights and has lost boosters on its suborbital tests. Even their nearest milestone, getting 1 gigawatt up by late 2027, requires a launch every 2 to 3 days. The rocket bottleneck is just incredibly severe. But, people in the industry are endlessly arguing about dollars per kilogram to orbit. So let's bypass that debate entirely. Let's run a fun little thought experiment using rigorous open source financial models, and let's set the launch cost of the Starship rocket to absolutely 0. Just imagine a magic free elevator to space. No launch cost whatsoever. Does the business case close then? Here is the ultimate crazy twist. Even with a magic free elevator to space, orbital compute still loses to a conventional ground build by more than 2 to 1. Building 1 gigawatt in orbit costs roughly $36 billion, while doing the exact same thing on the ground in Texas costs about $16 billion. So the rocket? It was actually never the binding constraint. It was just the most photogenic one. The real problem is where all that money goes once the hardware is actually up there. So why is it so ridiculously expensive to run this in orbit? Well, because you're launching 670,000 completely independent, self-powered, non-serviceable buildings where a technician is never, ever going to visit. On Earth, if a GPU dies, a tech swaps it out in 5 minutes. In space, that server is dead forever. This completely slashes the asset's life down to just 5 years, compared to 15 years on the ground. And because of that, it forces you to launch 38% extra redundant hardware up front, just to compensate for the inevitable failures. Basically, every single dollar of incredibly expensive silicon has to earn its return 3 times faster in space. All right, so if the rocket isn't actually the bottleneck, and the financial math doesn't even come close to working on paper, even with a free launch, we really have to take a step back. What was this massive 1 million satellite number actually for if it wasn't a rigid, practical engineering plan? Well, if we pull up the calendar, things get kind of fascinating. A really clear pattern emerges. Every single major StarMind disclosure lines up with uncomfortable precision alongside massive capital market events, rather than actual engineering milestones. That initial 1 million satellite FCC filing dropped the exact day after merger talks leaked. The super detailed AI-1 engineering video, released just 3 days before the largest IPO in history, and that massive NVIDIA partnership and Terafab factory announcement revealed exactly as the post-IPO lockup period was expiring, which unlocked $99 billion in shares. Now, we aren't stating intent here, but man, the timeline absolutely speaks volumes. So that timeline sets the stage, right? Now let's look at how Wall Street is digesting this massive spending spree, because the market tape tells a very clear story. Investors actually don't doubt the revenue at all. SpaceX posted an unbelievable 92% year-over-year revenue growth. But the market deeply, deeply doubts the massive capital expenditure. I mean, they dropped nearly $16 billion on AI infrastructure in a single quarter. This absolute flood of spending has led to a 54% stock drawdown from all-time highs. And it's created a huge divergence among analysts. You've got some pricing the stock at $62 and others way up at $160. There is just massive, genuine uncertainty about this huge orbital bet. Now, to be totally fair, impartially speaking, we have to look at the strongest possible case for the other side, the steel man argument. SpaceX's absolute strongest defense is a supply constraint argument. Right now, down here on Earth, getting permits and grid interconnects for massive new gigawatt data centers is becoming almost impossible. The power grids are totally topped out. So if ground capacity literally becomes unbuildable at any price, then paying a massive 2x premium for space infrastructure suddenly becomes the only winning hand. Being twice the price, but actually available, that always beats being cheap but physically impossible to build. And that brings us to one final really provocative question to take away from all this. Is moving data centers to space really a story about brilliant engineering efficiency? Or is it a desperate, trillion-dollar play for the absolute last available unpermitted energy in the universe? The physics might barely hold up, but the economics tell a story of a company betting that Earth is simply out of room. Definitely something to keep in mind the next time you look up at the night sky.